Okay, so we're going to go over a bit of proof by induction for a couple more examples in this little video. So mathematical induction is a method of proof that only can be used to prove propositions, formulas, mathematical statements for integers or natural numbers. Terminology around it is a little bit confusing, but basically what we're saying is we've got a mathematical function. It's defined for some integers. Let's call it P of n. It's defined for some integers or natural numbers, and it starts at a particular integer, a. Let's call that a, which means basically this proposition or function is going to be applicable usually for n is greater than or equal to a for all values of n that are either integers or potentially natural numbers. So you need to read what the question says, okay, to set up the proof. And we start off with a classic step for mathematical induction. It's called the base step, and sometimes it's referred to as the base case. So starting from the very first value that we're saying the formula is true for, we want to show by substituting a into that formula that it is also true. That's called the base case or the base step. We want to establish that the proposition is true for the starting value that we're saying it is true for, which is n equals a. And then we make an assumption. We make an assumption that the proposition or formula will be true for n is equal to k. That's what this means here. N is equal to k here. That's what that means. Where k is some integer that's larger, greater than or equal to that starting value a. And then by implication, we show that the function or formula is also true for n is equal to k plus 1, based on our assumption and findings about the previous case where n was equal to k. And then our conclusion by this implication, if we're able to establish that implication is, well, believable, credible, follows the rules of algebra, then we can say that the proposition or formula is true for all integers that are greater than or equal to that starting case of a. Okay, so let's do another example here. So we have an example here that we're going to use mathematical induction on. So we're already guided here. We're told we have to use induction. Now, if we weren't given a choice, we would have to look at this problem and think about all the other proof methods we could apply. But because in this one we're told to use induction, well, basically we have to follow that. So this is asking us to consider some mathematical notation or formula. This is a recurrence relation for working out the next value in a series. And it's basically saying, well, the nth plus 1th value is equal to 3 times the previous value plus 2. And here are some starting values. T0, T subscript 0 is equal to 0, and T subscript 1 is equal to 2. And this is the formula that we need to prove applies for this particular recurrence relation when it starts off with these two values. Okay, so if we're asked to do this by mathematical induction, so we have to follow those 3 steps, which is the base case, assume it's true for n equals k, and then using n is equal to k, we can imply that it is also true for the next integer or natural number, and then we could give our conclusion about how our proof worked out. Okay, so the base case in this one has 2 base cases. It's got one base case of 0 and another base case of n is equal to 1 here. Just erase that, I didn't mean to scribble that out. Okay, so let's proceed. Okay, so step 1 is the base case, except there's 2 this time, base cases. So we want to say, okay, does our proposition hold when n is equal to 0? That's this one here. Let's put it into the formula. T of 0, that's the formula. This formula here is the one we want to prove. A lot of things going on. Is that equal to 3 to the power of 0 minus 1? Is that equal to T of 0? Is that equal to T of 0? Is that equal to 0? You can see that it pretty much will be, because that's going to be 1 minus 1, which definitely equals 0. The second base case here is for n is equal to 1. For n is equal to 1, basically we're saying, well, does T1 equal 3 to the power of 1 minus 1? Now T1 was said to be equal to 2, so does it equal 2? Okay, you can see pretty much 3 minus 1 is going to equal 2. So that's correct. So both base cases are correct. Step 1. Step 2, we're going to assume it's true for n equals k. So we're going to assume that this correctly works out T of k. And if you want to put it in propositional notation, we're assuming it's true for k. So T of k, we're saying, is going to be true when we substitute it into this formula. We are going to get the k term by using this formula. So that's assume that's true. Okay, so the next step, we're going to use the implication. We're going to use the previous result to imply that P of k plus 1 is also true. So now we need to have a look at when we're putting in k plus 1 here, when we're going to get this expression. T of k plus 1, the k plus 1 term, is that equal to 3 k plus 1 minus 1? That's the bit we have to prove. And we have to use this previous result to help us do that, which is not always easy because you have to do a lot of algebra. Okay, so we need to do a lot of algebra to be able to do that. Let's see if we can do this algebra. So is that going to be true? The series, we've got T of k plus 1 over here is equal to 3 times T of k plus 2. We're assuming that that is true because that is in the if true part before the then. Okay, so we're assuming that is true. So we want to make sure that we get the same answer. Okay, so let's park that over there for a second. That's using the P of k. We want to see if that's going to be true. We know that over here, T of k plus 1, if that is true, we've worked out what T of k is. That's equal to 3 times 3 of k minus 1 plus 2. Okay, so putting that in there, that's going to be helpful to try and prove the implication here. So this expanding these brackets, well, 3 times 3 to the power of k is 3 to the power of k plus 1. 3 times negative 1 is negative 3 plus 2. It's looking really good so far. So that is now 3 to the power of k plus 1 minus 1. And how about that? That is exactly the same as what we get from the formula. So that's one way of showing it's true. The beauty about mathematical induction, so that's one way, we showed that that was true. That's one way, and that's perfectly valid. There's another way we could show it was true, just to make life a bit more complicated. We could have gone to this formula straight away and said, well, if we expand that out, k plus 1, we've got that minus 1, that's equal to 3 times 3 of k. Having a look at this formula, 3 times 3 of k is 3 of k plus 1. Okay, we've got a problem with that 3. If we put any number next to it, we're trying to get minus 1. That's what we're trying to get. We're trying to get this expression up here. So we're trying to get the inductive step in there somehow. So that's going to be 3 times 3 of k, which is 3 of k plus 1. That's good. But then 3 times negative 1 is negative 3, which is not good. So we need to add 2 here. Okay, so if we do that, we're going to then show that we indeed have proven this to be true, because we have 3 times t of k here plus 2, which is also going back to the recurrence relation. So we've proved it 2 ways by using the recurrence relation, which is said to be always true because it's before the then statement. It's the assumed true thing. We've shown that that's true. Okay, so we're all good. Now we just need to make the conclusion. We're able to do it 2 ways. This is way, we did it this way. That was plan A. And then we did it this way, which was plan B. And then we're able to show it with the 2 ways. So our conclusion is, since the base case was true, base cases were true, and P of k assumed true, we were able to show P of k plus 1 by mathematical induction. Okay, that took a long time, didn't it? And hopefully you were able to follow that. Okay, let's try it on another one here. This one's going to be slightly harder, I think. So this one is, we've got a geometric series this time. So this one, you can see it's a geometric series. Everything's being multiplied by 3 to some power. So that's 2 times 3 is 6. 6 times 3 is 18. And then to get to the nth term, that's 2 times 3 to the power of n minus 1. So this is saying that this formula is the summation for this particular geometric series. And if we test it out, we've got some partial sums. We can test it out for the first term. That's looking good. For the first term, that's correct. The formula applies really well. That's 3 to the power of 1 minus 1. That does equal 2. We're all good with that. If we have a look at the next one, that's adding 2 plus 6. Let's pop that into the formula. That's 3 to the power of 2 minus 1. That's going to be equal to 9 minus 1, which is 8. That matches that. And then if we keep on going, the first 3 terms add up to 26 just by looking at the geometric series here. If we just apply the formula, that's 3 to the power of 3 minus 1, and that does equal 26. So it's looking pretty good. All right, that's looking good. Okay, so we've got a formula that we know works for geometric sums. And we didn't have to prove it was true. We just assumed it was true. So now we're going to try and see how we're going to go with this. This particular formula ends up simplifying to be this expression based on this starting value and this ratio used for the geometric series. Let's try that out. So S of n, when a is equal to 2, that's going to be 2. And then we've got r is equal to 3 to the power of n minus 1 over r minus 1, well, that's 3 minus 1. That's equal to 2, so those 2's will cancel, and we end up with that formula. How about that? So I want to prove that that formula is correct now. We've got the formulas that we memorized from sequences and series, but we're going to do this by mathematical induction now. Okay, so first thing we need to do is identify what the base cases are. So I guess we can say that the base case is when n is equal to 1. We already kind of did that up here. So the base case, if we want to put the propositional notation, that's the base case, or base case was where n is equal to 1. That's the smallest term here, because this geometric series is only applying for n is greater than or equal to 1, where n is a natural number. It's pretty much our implication for this geometric series. So the base case, n is equal to 1. Let's plug that into the formula. 3 to the power of 1 minus 1, that equals 2, and that is true. That is the sum of the first term, which equals the sum of the first term, which is 2. All good. Okay, so we're going to assume that this formula is correct for the adding up k values in this geometric series. So we're assuming it's correct for n is equal to k. Basically, we're saying that 3 to the power of k minus 1 is equal to this geometric sum for k. We're assuming that to be true. Okay, let's have a think about this. That is assumed true. Assumed to be true. If we want to get s, the next value in the geometric sum, we know we need to add to this value that we have, we need to add the next value. This is s of k. We need to add the next value, which we know from the formula is plus 2, 3 to the power of k plus 1 minus 1. 3 to the power of k plus 1 minus 1. Okay, that's what that formula says up there, which is going to be, what's that going to be equal to? That's going to be 2 to the power times 3 to the power of k. All right, that is an interesting thing to look at. All right, let's think about that, and let's try by implication. We're going to do the inductive step. We're going to say that assuming it's true for p of k, we're going to assume it's true for the next integer. We're going to say, well, s of k plus 1 equals 3 of k plus 1 minus 1. Is that true? Can we use our assumption, our inductive step assumption here to show that that is true? Assume true. Are we able to make that look like this one over here? I think we can. Let's have a look. So we've got, if we expand all of this out, let's have a look. We've got 3 of k minus 1 plus 3 of k plus 3 of k. And that's going to work out to be 3 times 3 to the power of k minus 1, which, what do you know, is actually 3k plus 1 minus 1, which is exactly the same as this formula is showing here. So we're able to show it's true. So hence, by mathematical induction, assuming the proposition is true, we were able to show that it was also true for the next integer or next natural number. We were also able to show that was true. And that implies that it's true for all n natural numbers. So P of n is true for all n natural numbers. Okay. So, long video. I'll be able to edit it. So let's have a look at all of that in summary. It is not easy. So mathematical induction relies on some basic steps and some basic properties of the mathematical statement that you're trying to prove. First of all, the mathematical statement you're trying to prove will only be applicable to integers or natural numbers usually, and there's usually a starting number. And we need to prove the base case first, and then by induction, for all k, show that the inductive case applies, and that means that if we use the fact it's true for n equals k, we can then imply it's also true for k plus 1. So here are the steps. Verify the truth of the statement for the smallest case, n is equal to a. That'll be written up in the problem saying what the range of the problem is. In the inductive hypothesis, we're going to assume that the statement is true for n is equal to k, where k is some integer or natural number larger than or equal to a. Then in the inductive step, we use the information we gathered from the inductive hypothesis, that's when it was n was equal to k, to show that the statement also holds with where n is equal to k plus 1. And then in conclusion, since the statement for all natural numbers or integers has been shown to be true for the base case, n equals a, assume true for the kth case, where n is equal to k, and then shown to be true for n equals k plus 1, then by mathematical induction we have shown that the proposition is true for n, which is all natural numbers that are greater than or equal to a, which was the base case. So you need to do all 4 steps, and you need to be clear and have nice working out. Thank you.